Hello, everyone. I'm Losey, and on behalf of my collaborators, I'm excited to present our work on shared autonomy with learned latent actions. When people living with physical disabilities interact with assistive robots, such as wheelchair and robotic arms, they're faced with two challenges. First, they need to control the high-dimensional dexterous robot to reach towards their desired goal. And second, once the arm gets to that goal, they need to precisely orchestrate the end effector to manipulate objects. In our prior work, we addressed the first challenge. We learned the latent actions that enable users to intuitively guide assistive robots towards their high-level goals. Hong here is using our algorithm, which makes high-level reaching much smoother than directly teleoperating the end effector. But even with this intuitive embedding, precise manipulation is still hard. In this paper, we combine our latent action approach with shared autonomy in order to enable precise assistive manipulation. Let's say you're trying to eat dinner. You control an assistive robot arm. The robot has a belief over the different goals on the plate. This belief captures the robot's confidence in which high-level goal you want to reach. As you start moving towards the rice, the robot updates its belief. And similarly, moving towards the tofu causes the robot to become confident that what you really wanted was that tofu. We propose incorporating this belief within a learned embedding that maps low-dimensional human inputs to high-dimensional robot actions. Let S be the robot state, A be the robot's high-dimensional action, and B be the belief. We start by collecting a set of offline demonstrations. We then embed these high-dimensional demonstrations into a latent action space. Because this latent space is low-dimensional, it's suitable for users to control with a joystick. The robot decodes the meaning of the user's latent action based on its current context. This context includes the system state, as well as the robot's belief over high-level goals. Ultimately, the robot maps the user's low-dimensional input to a high-dimensional action. And this reconstructed action should match the demonstrated actions. For example, here the robot has learned to pour and move across the table. Under this approach, the robot's belief determines what the user's inputs control. So at the start of the task, when the robot is not very confident in any goal, user inputs map to high-level reaching motions. As the human guides the robot towards their goal, the robot becomes more confident. And the user's inputs gradually shift to control fine-grained motions at that goal. We show that this approach ensures the robot converges to the human's high-level goal, even if the human is bad at controlling the robot. Applying the Autonomy stability analysis, the error between the robot's state and the human's goal is uniformly ultimately bounded. And the size of that bounding ball decreases as the robot's confidence in the human's goal increases. But the human might mess up and lead the robot towards one high-level goal before changing their mind. If the robot has already converged towards the first goal, how do we ensure that it's not stuck and unable to change goals? We address this problem by encouraging entropy in the latent action space. Here's an example of our desired behavior. A Boltzmann rational simulated human is controlling the robot. They initially move towards the red cup and then change their mind so that the purple cup becomes their true goal. On the left, we show a simulated human interacting with a latent space that does not encourage entropy. If the simulated human changes their mind early in the task, let's say at time step 3, they can reach their true goal. But if the human changes their mind after the robot becomes confident that they want to reach the red cup, they get stuck. And this only gets worse the longer they wait before changing their mind. Encouraging entropy addresses this problem. On the right, the simulated human is always able to use latent actions to change goals, even if the robot is convinced in their initial goal. We conducted a user study to test if people were able to perform precise manipulation on an eating task. Here I show retargeting, one of the baselines from this user study. In this baseline, the user directly controls the position and orientation of the end effector through a joystick. You can see that they never really change the alignment of the end effector throughout the task and are almost always in a stabbing orientation. Here's that same user with our proposed approach, latent actions and shared autonomy. You'll notice that the robot helps the user reach and maintain the 3 high-level goals in this space, the marshmallow, the icing, and the rice. And the robot enables the human to perform precise manipulation and alignment at these different goals. So they stab marshmallow, but scoop the icing. To summarize, we combine low-dimensional embeddings with goal-directed shared autonomy to enable precise manipulation in assistive tasks.